a million miles from Earth, in the deep cold between worlds, a mirror of gold floats in slow orbit around the sun. It is not anchored to anything. It moves on a long looping path, suspended in a place where the gravity of the sun and the gravity of the Earth balance just enough to let it drift, almost weightless, for years on end. The mirror is unfurled like a flower made of metal hexagons, 21 feet from edge to edge. Behind it, a kite of silvery film as wide as a tennis court keeps it cool, shading the optics from the sun's heat. And every minute of every day, it gathers light that has been traveling for billions of years. That telescope is the James Webb Space Telescope. Since the summer of 2022, it has been quietly opening the deepest parts of the universe to human eyes for the first time. And as the data has come back, image by image, spectrum by spectrum, something unexpected has been happening. The universe Webb is showing us does not quite match the universe we expected to see. Some of the galaxies are too large. Some are too old. The numbers, in places, do not line up with the equations. The first equations were Einstein's. More than 100 years ago, he wrote down a description of gravity that has shaped almost everything we believe about space, time, and the expansion of the universe. From those equations, generations of physicists built a model of the cosmos so detailed that until recently, it seemed almost complete. We knew, or thought we knew, when the first galaxies formed, how the universe had evolved and how fast it was expanding right now. The map was drawn. The story was, in its broadest strokes, settled. And then Webb's data started arriving. Tonight, we will take our time with that data. We will look at what Einstein's universe predicted, what Webb is actually seeing, and what the gap between the two might mean. None of this is fully understood yet. The leading scientists in the field disagree about what to make of it. We are, in a quiet way, watching a piece of physics history unfold in real time. Settle in. The story is long, the pace is slow, and the universe, as always, is in no hurry to give up its answers. The universe Einstein gave us was not the one most people had imagined before. In 1915, when he completed his theory of general relativity, the dominant picture of the heavens was still, in many ways, a Newtonian one. Space was a fixed stage. Time ticked uniformly everywhere. Gravity was a force that pulled objects toward each other through empty distance. Stars, in this older picture, hung in their places, and the universe as a whole was thought to be static, unchanging, eternal. Einstein replaced that picture with something stranger, and, in the end, much closer to what we now believe to be true. In his theory, space and time were not separate. They were woven together into a single fabric, four-dimensional, and that fabric could bend and stretch. Mass, in this picture, did not pull objects with an invisible force. It curved the space around it, and the curvature was what we experienced as gravity. A planet orbits a star, not because the star is tugging on it, but because the star has shaped the space nearby, and the planet is following the straightest possible path through that shape. For a few years, Einstein himself was reluctant to follow his own equations all the way to their conclusion. When he applied them to the universe as a whole, they suggested that the universe could not be static. It had to be either expanding or contracting. This was so contrary to what astronomers of the time believed that he added a term to his equations, the cosmological constant, designed specifically to hold the universe still. He would later, in private, call this his greatest mistake. It was Edwin Hubble, working at the Mount Wilson Observatory in Southern California, who showed in 1929 that the universe was not static. He observed that distant galaxies were moving away from us, and the farther away they were, the faster they were receding. The universe, it turned out, was expanding. Run that expansion backward in your mind, and you arrive at a moment when everything was packed into a single, dense state. That moment, eventually, would come to be called the Big Bang. From the 1960s onward, the evidence for an expanding universe with a hot, dense beginning kept accumulating. The cosmic microwave background, the faint afterglow of the early universe, was discovered in 1965 by two radio engineers at Bell Labs named Arno Penzias and Robert Wilson, who were trying to figure out why their antenna kept picking up a strange hiss. That hiss turned out to be light from when the universe was only a few 100,000 years old, stretched and cooled by billions of years of expansion, until it had drifted down into the microwave part of the spectrum. Once that discovery was made, the Big Bang model became the standard. But there were still gaps. The amount of matter we could see in galaxies could not, by itself, hold those galaxies together. Stars on the outer edges of spiral galaxies were moving so quickly that by the equations, they should have flown off into space long ago. Something invisible was holding them in place. We called it dark matter, though no one knew what it was. And in 1998, two teams of astronomers studying distant supernovae found that the universe's expansion was not slowing down as everyone had expected. It was speeding up. Something was pushing space apart, gently but persistently on the largest scales. We called that dark energy, again without really knowing what it was. Out of all of this came what is sometimes called the standard model of cosmology, or the lambda CDM model. Lambda, the Greek letter, stands for dark energy, since it behaves mathematically much like the cosmological constant Einstein once added and then regretted. CDM stands for cold dark matter, the slow-moving, invisible substance that helps galaxies form and hold together. In this model, the universe is made of roughly 5% ordinary matter, the kind that forms stars and planets and human beings. Roughly 27% of it is dark matter, and the remaining 68% is dark energy. It is a strange thing to sit with. Almost everything we can see, every star, every planet, every cloud of glowing gas, all of it makes up only a small fraction of what is out there. The vast majority of the universe is invisible to us, and it acts on space and time in ways we describe only through their gravitational effects. We see what it does. We do not yet see what it is. This was the picture, in broad strokes, when Webb launched. It was a beautiful and remarkably successful model. Predictions made decades earlier had been matched by observations. The early universe had been mapped in extraordinary detail by satellites called COBE, WMAP, and Planck, each one improving on the last in the precision with which it measured the leftover light of the Big Bang. The shape of the universe, the rough age of it, around 13.8 billion years, the relative proportions of its ingredients, all of these had been measured. There were still mysteries, but the foundation seemed solid. The James Webb Space Telescope was designed and built over the course of more than 2 decades, and from the beginning, it had a particular goal in mind. It was meant to see the universe as it was when it was young. This goal sounds simple. The way it works is anything but. Because the universe is expanding, light from distant galaxies is stretched as it travels through space. The farther away a galaxy is, the more its light has been stretched. By the time the light from the most distant galaxies reaches us, it has shifted from the visible part of the spectrum into the infrared, into wavelengths longer than what the human eye can see, longer than what most ground-based telescopes can comfortably observe. To see the first galaxies, you need a telescope tuned to the infrared. And to keep that infrared light from being drowned out by the warmth of the telescope itself, you need to keep the instrument extraordinarily cold. That is why Webb is where it is. Roughly 1 million miles from Earth, at a place called the second Lagrange point, where the gravity of the Earth and the Sun balance in a useful way. Webb sits there in a gentle, looping orbit, with its giant sun shield always facing toward the Sun. The 5 layers of that sun shield, each one as thin as a human hair, drop the temperature on the cold side of the telescope to around minus 370 degrees Fahrenheit. In that cold, the instruments can detect faint infrared light from across the universe without being overwhelmed by their own heat. Webb's primary mirror is 6.5 meters across, about 21 feet wide. It is made of 18 hexagonal segments, each one coated in a thin layer of gold to reflect infrared light efficiently. The whole structure was folded up like origami inside the rocket fairing for launch, then unfolded over a period of 2 weeks once it had reached deep space. Every step of that unfolding had to work. There were hundreds of single points of failure, places where one stuck mechanism could have ended the mission. None of them failed. By the summer of 2022, the mirror had been carefully aligned, the instruments had been calibrated, and Webb began returning its first scientific images. Those first images were beautiful, a field of distant galaxies, sharper than anything the Hubble Space Telescope had ever returned. A planetary nebula glowing in colors no eye could have seen. The Carina Nebula, where new stars were being born, rendered in such detail that you could trace individual jets of gas where infant suns were just beginning to take shape. The public attention was, briefly, enormous. But it was the science that came after the pretty pictures that began to surprise people. Webb's most ambitious deep field programs go by names that sound when you encounter them for the first time, like acronyms invented by committee. JADES, the JWST, Advanced Deep Extragalactic Survey. CEERS, the Cosmic Evolution Early Release Science Survey. Cosmos Webb. Primer. Each of these is a long, patient observation of a small patch of sky, gathering light for hours and hours, sometimes days, in order to detect galaxies far beyond what any previous instrument could see. When you point Webb at a patch of sky that looks empty in older images, what comes back is not emptiness. The patch fills with galaxies. Some are familiar in shape, spirals and ellipticals seen from various angles. Some are oddly distorted, shaped like clumps or smears or arcs. And some are dim, red points, almost lost against the background, that turn out, on closer analysis, to be galaxies from the very young universe. From the first few 100 million years after the Big Bang. The reason these galaxies look red has nothing to do with their color when their light was first emitted. It has to do with how far that light has traveled. Most of these galaxies, when their stars were shining, were emitting blue and ultraviolet light, the kind young hot stars produce. But by the time that light reaches Webb, it has been stretched so far by the expansion of the universe that it arrives in the infrared. the redder a galaxy appears in Webb's data, the longer its light has been on its way, and the deeper into the history of the universe we are looking. By 2023, Webb had found galaxies that, by these measurements, must have existed when the universe was around 300 million years old. That is younger than almost anyone had expected to see. In the Lambda CDM model, the first galaxies were supposed to be small, faint, and forming slowly out of the early matter. What Webb began to find, though, was something else. Some of the galaxies Webb has found in the early universe are too big. This sentence, when you first encounter it, does not quite make sense. How can a galaxy be too big? The answer is that in the standard model, galaxies grow over time. They start small, gathering gas, forming stars, merging with other small galaxies. The first galaxies, in the model, should be modest, a few 100 million stars, gathered into a loose, irregular shape. Galaxies the size of our own Milky Way, with hundreds of billions of stars and the elegant spiral structure we associate with mature systems, are supposed to take billions of years to develop. But some of the galaxies Webb is seeing, in the first few 100 million years after the Big Bang, appear to contain stellar masses that should not yet have had time to accumulate. The earliest version of one of the most striking results came in 2023 from a team led by Ivo Labbé, then at Swinburne University in Australia, and his colleagues. They had been examining Webb data from the CEERS survey, looking at a set of unusually bright red points in the sky. Using the colors of the light at different infrared wavelengths, they estimated how far away the galaxies were and how massive. The conclusions were striking. 6 galaxies, according to the analysis, appeared to have stellar masses many billions of times that of our Sun, in some cases close to the mass of the Milky Way today. They appeared to have existed when the universe was only around 500 to 700 million years old. That is roughly 4% of the current age of the universe. In the Lambda CDM model, the matter available at that early time should not have been able to assemble into galaxies that massive that quickly. The arithmetic did not work. When the result was published in the journal Nature, it caused something of a quiet stir among cosmologists. The headline in some places was that the universe was breaking the standard model. The reality was more measured. The analysis depended on a number of estimates and assumptions, especially about the kinds of stars these galaxies contained and how much light those stars were emitting. There were many ways that the apparent masses could turn out to be wrong, or at least less extreme. But even with conservative assumptions, the galaxies were larger and brighter than expected. In the months and years that followed, more careful follow-up observations have refined the picture. Some of those very bright early galaxies turned out, on closer inspection, to be less massive than first thought. Some of them turned out to host black holes at their centers that were emitting much of the light, so that what looked like an enormous mass of stars was, partly, the glow of accretion around something invisible. Other galaxies have been confirmed as being almost as old and almost as massive as initially estimated. The tension has not disappeared. It has shifted and softened and become more nuanced. There is also a related puzzle. Some of the early galaxies are not just unexpectedly massive. They are unexpectedly mature. They contain dust, the small grains of carbon and silicate that take time to form in the universe. They contain heavier elements, the kind produced inside earlier generations of stars and then scattered outward when those stars died. To find such elements in galaxies only a few 100 million years after the Big Bang means that, by then, generations of stars had already lived and died, releasing their material into the surrounding gas, and that gas had already been gathered and reformed into new structures. In one galaxy now known as JWST-GS-Z14-0, observed at a redshift of about 14, the light Webb is detecting was emitted when the universe was only around 290 million years old. That is roughly 2% of its current age. The galaxy is unexpectedly bright. It is unexpectedly large for its time, several hundred light years across. It is, by the measurements available, well on its way to becoming the kind of structure that the model had expected to take far longer to form. None of this means that the standard model is wrong. Not yet. But it means that the model has more work to do. The first galaxies, by what Webb is showing us, formed earlier and grew faster than the simulations had predicted. Either the early universe was richer in star-forming material than we thought, or stars in the early universe formed more efficiently than they do now, or something in the model of how matter clumps together at very early times needs to be revised. Several explanations are on the table. One is that the first generations of stars were unusually massive, often hundreds of times the mass of our Sun. Massive stars are extremely bright. So if early galaxies were full of them, those galaxies would look much brighter than expected, even if their total mass were modest. Another explanation is that early galaxies turned a higher fraction of their gas into stars than later galaxies do. This is sometimes called a high star formation efficiency. A third is that some of what we are seeing is not pure starlight at all, but light from massive black holes feeding on infalling material in the centers of those young galaxies. Each of these explanations works in some cases and not in others. The picture, at the moment, is one of many small puzzles, each requiring its own careful analysis, rather than one single dramatic crisis. That is, in its own way, how science usually moves. There is a second, deeper puzzle that Webb has brought into sharper focus, and it has been quietly causing arguments in cosmology for longer than the early galaxy question. It has to do with how fast the universe is currently expanding. The rate of expansion has a name. It is called the Hubble constant, after Edwin Hubble, the astronomer who first measured it. It tells us how quickly, on average, galaxies are moving away from us as a function of their distance. The unit of measurement is somewhat awkward, kilometers per second per megaparsec. A megaparsec is roughly 3.3 million light years. So the Hubble constant, in those units, tells us how many kilometers per second of recessional speed a galaxy gains for every megaparsec of distance from us. For most of the 20th century, the Hubble constant was poorly known. Estimates ranged from around 50 to around 100 kilometers per second per megaparsec, depending on whose measurements you trusted. The reason for the wide range was that measuring the constant requires two things: a distance to a galaxy and a velocity. Velocities are relatively easy to get by measuring how much the light from a galaxy has been shifted toward the red end of the spectrum. Distances are much harder. You need a reliable way to know how far away something is. For nearby galaxies, the most trusted distance markers are stars called Cepheid variables. Cepheids are stars whose brightness varies in a regular cycle, and the length of that cycle is tightly related to their true average brightness. If you know how bright a Cepheid really is, and you can measure how bright it appears from Earth, you can calculate how far away it must be. This relationship was first noticed by an astronomer named Henrietta Swan Leavitt, working at Harvard in the early 1900s, examining photographic plates of stars in the Magellanic Clouds. She was paid 25 cents an hour, and she changed astronomy forever. Cepheids let you measure distances out to the closer galaxies. Beyond that, you need brighter markers, and the next step up is supernovae, specifically a kind called Type 1Ia, which are thought to all release roughly the same amount of light when they explode. By calibrating the Type 1A supernova against galaxies that contain Cepheids, you can build a distance ladder, with each rung extending a little farther out into the universe. Using this ladder, astronomers led in recent decades by Adam Rees and his team have measured the Hubble constant at around 73 kilometers per second per megaparsec, give or take a small uncertainty. This is, in a sense, the local rate of expansion. There is another way to measure the Hubble constant, and it is very different. It involves looking at the cosmic microwave background, the leftover light from the early universe, and inferring from the patterns in that light how fast the universe should be expanding today, given everything we know about its composition and evolution. The Planck satellite did this most precisely between 2009 and 2013. The number that came back was around 67 kilometers per second per megaparsec. That is a difference of about 6 kilometers per second per megaparsec between the two methods. It does not sound like much, but the precision of both measurements has become so high that the disagreement is statistically significant. The two numbers are, by their own error bars, incompatible. One of them, at least, is missing something. This disagreement is what cosmologists call the Hubble tension. It has been growing tighter and harder to dismiss for about a decade. There were once hopes that the difference would shrink as measurements improved. Instead, it has held its ground, and in some analyses, become slightly worse. When Webb launched, one possibility that some hoped for was that it would help reduce the tension. Cepheids, after all, are observed in the visible and near-infrared. Webb's superior resolution might show that some of what had been thought to be a single Cepheid was actually 2 or 3 stars blended together. If many of the Cepheid measurements had been slightly off in that way, the local distance ladder might shift downward, and the local value of the Hubble constant might fall closer to the value from the microwave background. The result has been the opposite of what was hoped. Webb has been used to re-examine many of the same Cepheids that Hubble observed. The conclusion of the most careful analyses, again led by Adam Rees and his colleagues, has been that the Cepheid measurements were essentially correct. The local Hubble constant is still around 73. The tension is still there. And now there is one fewer place where the error could have been hiding. This has changed the conversation. As long as it was possible that the local measurements were subtly mistaken, many cosmologists held out hope that the tension was an artifact, a measurement issue that would clear up over time. With Webb's confirmation of the Cepheid distances, that hope has narrowed. The tension may be telling us something real. So where does the difference come from? If the tension is genuine, it points to something missing or incorrect in the standard picture. There are a few possibilities, none of them simple. One is that the early universe had a brief additional source of energy that changed its expansion history in a way the standard model does not include. This idea is often called early dark energy. It is, mathematically, a way to make the microwave background measurements compatible with a faster current expansion. But it requires inventing a new ingredient in the early universe, something that switched on for a short time and then faded. Another possibility is that dark energy itself is not constant. The lambda in lambda CDM is named after Einstein's cosmological constant, a fixed value that does not change with time. If dark energy is instead something that evolves, growing weaker or stronger as the universe ages, the expansion history changes, and the tension might be resolvable. A third possibility is that something in the model of dark matter is slightly different from what is assumed. A fourth is that gravity itself, at the largest scales, does not behave exactly as Einstein's equations predict. Each of these would be, in its own way, a small revolution. There is a quiet beauty in how these questions are being investigated. Far from any dramatic moment of discovery, the work happens in spreadsheets, in code, in long late-night discussions among collaborators in different time zones. A galaxy is examined. Its spectrum is fit. Its distance is estimated. Its mass is recalculated. The result is compared against the model. The disagreement is noted. The team writes a paper. The paper is reviewed. Other groups try the same analysis on the same data and on different data. And slowly, over months and years, the picture sharpens. In the case of the early galaxies, several survey teams have now confirmed each other's basic findings. The galaxies are there. They are old. Some of them are unusually bright for their age. The interpretation is the part that remains under negotiation. New simulations have been run, with different assumptions about how stars form, how much dust they produce, how much of the gas in early galaxies turns into stars, rather than being expelled or pulled into central black holes. Some of these simulations can produce galaxies like the ones Webb is seeing. Others cannot. The fit between the model and the data is now where most of the work lies. In the case of the Hubble tension, the work has become almost forensic. Adam Rees and his team have published a series of papers using Webb data to examine, in extraordinary detail, the Cepheid stars in nearby galaxies. They have looked at the effect of crowding, the way that a bright star might appear brighter still because of unresolved companions nearby. They have looked at metallicity, the chemical composition of the stars, which affects their intrinsic brightness. They have examined dust. In each case, the corrections have been small. The local Hubble constant has not moved much. The tension has remained. Other groups have approached the problem from different angles. There are distance measurements that do not use Cepheids at all. One method uses the tip of the red giant branch, a kind of standard candle based on the brightness of stars at a particular stage of their life. Another uses the surface brightness fluctuations of elliptical galaxies. Another uses gravitational waves, the ripples in space and time produced by merging neutron stars and black holes, which give an absolute distance scale if their host galaxies can be identified. None of these methods agree perfectly, but most of them point toward a higher local value of the Hubble constant, somewhere in the low to mid-70s, in tension with the value from the microwave background. There is, at this point, a real sense in cosmology that something will eventually have to give. Either the local measurements all share a common, deeply hidden flaw that no one has yet identified, or the model of the universe used to interpret the microwave background needs to be modified, or both. One particular kind of modification that has been getting more attention recently has to do with the cosmological constant itself. In 2024, results from a survey called the Dark Energy Spectroscopic Instrument, located at Kitt Peak in Arizona, suggested that dark energy might not be constant after all. By measuring the patterns of galaxies across vast volumes of the universe, that team produced data that, when combined with other observations, hinted that the strength of dark energy may have been slightly different in the past than it is today. The result is not yet definitive. The error bars are large. But it is one of the first observational hints that the lambda in lambda CDM might need to be replaced with something that changes over time. If dark energy is not constant, the implications would be considerable. The far future of the universe depends on the behavior of dark energy. A constant dark energy leads to a universe that continues to expand forever, growing colder and emptier across enormous spans of time. A dark energy that grows stronger could eventually pull galaxies, then stars, then atoms apart in what is sometimes called a big rip. A dark energy that grows weaker could allow gravity to slow the expansion and, perhaps, reverse it. None of these scenarios is imminent. The timescales involved are larger than the universe's current age. But the long-term shape of history depends on the answer. For now, all of these possibilities are being examined together in parallel. There is a sense in which the cosmology community is engaged in something like a long, patient process of measurement, where each new data set narrows the range of plausible models a little further. Webb's role in this process is enormous. It is providing some of the most precise distance measurements ever made, and it is opening up parts of the history of the universe that no previous instrument has been able to see clearly. There is another category of observations that Webb has brought into focus, and it sits quietly alongside the early galaxy puzzle and the Hubble tension. It has to do with black holes in the early universe. For decades, astronomers have known that the centers of most large galaxies contain supermassive black holes, objects with masses ranging from a few million to a few billion times that of our Sun. The black hole at the center of our own Milky Way, called Sagittarius A star, weighs about 4 million solar masses. The one at the center of the galaxy, Messier 87, which a global network of radio telescopes famously imaged in 2019, is more than 6 billion. These objects are believed to have grown over billions of years, swallowing gas and stars and merging with other black holes as their host galaxies grew around them. The question, for many years, has been how the first supermassive black holes got started. In the standard picture, a black hole begins small, when a massive star runs out of fuel and collapses at the end of its life. The resulting black hole might weigh only a few tens of solar masses. From there, it grows by gathering matter and merging with other black holes. But this growth takes time. And the more carefully we have looked at the early universe, the more clearly we have seen black holes that, by every reasonable estimate, should not yet exist. Even before Webb, quasars had been found at very high redshifts, extremely bright points of light that turn out to be supermassive black holes feeding on enormous amounts of gas in the centers of young galaxies. Some of these quasars, observed in the first billion years of the universe, contain black holes weighing more than 1 billion solar masses. To grow that quickly from a stellar mass starting point, even at maximum theoretical rates of accretion, would push the available time to its limit. Something, perhaps, was helping these early black holes form bigger and faster than the simplest model allows. Webb has now found more of them, smaller and farther back. Among its discoveries are a population of compact red objects, sometimes called little red dots, that appear to be galaxies with extremely active black holes at their centers, observed when the universe was less than 1 billion years old. The black holes inside these dots, by the analyses available, appear to be unusually massive for their host galaxies. In the modern universe, the mass of a galaxy's central black hole tends to scale with the mass of its bulge of stars. In these early little red dots, the black hole seems to outweigh the stellar mass by an unusually large fraction. The black holes are, in a sense, ahead of their galaxies. Several explanations are being explored. One is that the first black holes did not begin as collapsed stars at all, but as massive clouds of gas that collapsed directly into black holes weighing tens of thousands of solar masses, with no intermediate star phase. These so-called heavy seeds would have given the early black holes a substantial head start. Another is that some of what looks like black hole light is actually contamination from other sources, and the masses being inferred are too high. A third is that the early universe simply allowed faster black hole growth than the modern universe does, perhaps because gas was denser, or perhaps because there were fewer disruptions from the feedback of stars. As with the early galaxies, the picture is one of many small puzzles rather than a single dramatic crisis. But it is a reminder that the early universe was, in several different ways, more developed by the first few 100 million years than the standard model had led us to expect. There is something almost philosophical in the way these results are accumulating. We had built, over the course of a century, a picture in which the universe began smooth and simple, and gradually built itself up into the rich structures we see today. Galaxies came together slowly. Black holes grew slowly. Heavy elements were forged slowly, generation by generation of stars. And the broad shape of that picture is almost certainly correct. The microwave background does show a young universe that was extraordinarily uniform. The structures of the present universe did emerge from small fluctuations in that early density field. Stars do produce heavy elements. Black holes do grow. None of this has been overturned. What Webb is showing us is, instead, a faster early act. The first chapter of the universe, between the moment when the leftover light was set free and the moment when the first stable galaxies had clearly formed, seems to have been more eventful than we knew. Stars formed earlier. Galaxies grew larger sooner. Black holes weighed more than they should have. The universe, in a sense, was impatient with itself in ways we had not appreciated. This does not mean the laws of physics were different in the early universe. The laws, as far as we can tell, are the same now as they were then. What it does mean is that the conditions in the early universe, the density of gas, the abundance of certain kinds of stars, the way matter clumped together at very early times, allowed processes to run faster and to greater extremes than the modern universe permits. To understand exactly why requires understanding the early universe in much more detail than we currently do. And that is what Webb and its successors will continue to do. It is also worth pausing on what we are not seeing. Einstein's general relativity itself remains, in all of the ways it has been directly tested, in excellent agreement with the data. We have watched gravitational waves from merging black holes ripple through space and time exactly as the theory predicts. We have seen light from distant stars bend around the sun by precisely the amount the equations say it should. We have measured the precession of Mercury's orbit, the gravitational time dilation of clocks on satellites, the structure of the Milky Way's central black hole, all in agreement with the theory. What is being questioned is not Einstein's gravity. It is the larger model of the universe that we built on top of his gravity. The lambda CDM picture, with its specific ingredients in their specific proportions, was always a model, and models are made to be refined. Whatever Webb is showing us, it is unlikely to retire Einstein. It is, more probably, going to ask us to add a chapter to the book. There is also something gentle to notice in this whole story, which is how often the most surprising findings have come not from the headline results, but from the careful follow-up work. When Webb first started returning images of unexpectedly large early galaxies, the first impulse was to declare a crisis. The more measured response, which has been the response of most of the community, has been to ask slowly whether the measurements are right, whether the assumptions in the analysis are right, whether the simulations the data are being compared to are right. Most of the time, in physics, when something looks like it cannot be true, it turns out to be a problem with the measurement or the interpretation. Occasionally, it really is the universe doing something new. The hard work is in figuring out which is which. There are now thousands of galaxies in Webb's deep field data. Each one is being studied, in some cases by multiple independent groups. Each one tells a small piece of a much larger story. Some of those pieces fit easily into the existing framework. Some sit awkwardly inside it. Over the next several years, as the data accumulates and the techniques improve, the picture will continue to sharpen. There are also other instruments at work. On the ground, telescopes like the Atacama Large Millimeter Array in northern Chile have been observing some of the same distant galaxies, looking at them in the millimeter and submillimeter parts of the spectrum, where cold dust and certain molecules give off their own signatures. By combining Webb data with data from other telescopes, astronomers can build up a more complete picture of what each early galaxy looks like, what it is made of, and how it is changing over time. There are also gravitational lensing surveys, which use the bending of light by massive foreground galaxies and clusters to magnify the light of more distant objects. Some of the most distant galaxies Webb has seen have been seen through such natural lenses, their light magnified by intervening matter, so that what would otherwise have been too faint to detect can be examined in detail. These observations are themselves a beautiful confirmation of Einstein's equations, since the precise amount of bending is predicted by general relativity. The very instrument that lets us see into the deep past also confirms the framework we are using to interpret what we find. The most honest answer to the question of what all this means is that we do not yet know. We are in the middle of a process that has not finished. The data is still arriving. The models are still being updated. The arguments are still being held. Several papers a week are published on these questions, and the picture continues to shift. But we can sketch out what kinds of answers are possible. If the early galaxy puzzle resolves through better understanding of how stars formed in the young universe, then the standard model survives, refined and improved. The simulations get updated. The textbooks get revised. The basic lambda CDM picture remains intact. The lesson is that the first generations of stars were stranger and more efficient than we had given them credit for. This is, perhaps, the most likely outcome. It is also the least dramatic. It would not produce headlines. It would just mean that science worked. If the Hubble tension resolves through some unaccounted for systematic error in the local distance ladder, then again, the Standard Model survives, and we will have learned something important about the limits of our measurement methods. This was the hope when Webb launched. So far, that hope has not been borne out, but it remains a possibility. If the Hubble tension is real and it requires new physics, then something has to give. The most discussed candidates fall into a few broad families. There could be a new component of the early universe, the early dark energy mentioned earlier, that briefly altered the expansion history. There could be a slow evolution in dark energy, replacing the cosmological constant with something dynamic. There could be a modification to gravity at the largest scales, a small change to Einstein's equations that becomes noticeable only over the largest distances. There could be new properties of dark matter that have been overlooked. There could be a combination of small effects, each contributing a piece, that add up to the discrepancy. Most of these ideas are, in their own ways, beautiful. They are also, at the moment, mostly hypothetical. Each one needs to be checked against many independent observations, not just the Hubble constant. A new ingredient in the early universe must not break the very successful predictions of the microwave background. A modified gravity must agree with what we see in galaxies, in clusters of galaxies, and in the large-scale structure of the universe. A dynamic dark energy must be consistent with the supernova data, with the patterns of galaxies measured by the Dark Energy Spectroscopic Instrument and other surveys, with everything we know. What this means is that any real revision to Einstein's universe will not come from a single dramatic result. It will come from many results, gradually fitting together into a new picture that explains everything the old picture explained, plus the new tensions, with similar elegance. That kind of revolution is slow. It takes years. It takes the careful work of thousands of scientists. The history of physics offers some comfort here. Einstein himself did not overturn Newton. He extended Newton. The old equations still work beautifully in the regimes Newton studied. They become inaccurate only when you try to describe things moving close to the speed of light, or near very massive objects, or across very large scales. Whatever comes next, if it comes, will probably do something similar with Einstein. The current equations will remain accurate over the regimes where they have been thoroughly tested. They will be embedded in a larger framework that captures more, that handles the early universe, the very distant universe, and the largest scales more accurately. This is not the way science is usually told in popular stories. The popular stories tend to feature dramatic moments, lone geniuses, sudden flashes of insight. The reality is slower, more collective, more patient. It looks much more like Webb itself, gathering light night after night, in a quiet orbit 1,000,000 miles from Earth, with hundreds of researchers across many countries working in coordinated, careful steps to make sense of what comes back. There is also the possibility, which we should not exclude, that nothing in our current picture is fundamentally wrong, and that all of these tensions are real but small effects that the existing framework can accommodate with minor adjustments. The universe may simply be more complicated in detail than the simplest version of lambda CDM. The unknowns may be filled in not by a revolution, but by patient elaboration, by the slow addition of small corrections that bring the model closer to the data without changing its essential shape. We will not know for some time which of these paths the science will take. The data Webb is gathering now is part of the answer. The data the dark energy spectroscopic instrument is gathering is part of the answer. The next generation of ground-based telescopes, the Vera Rubin Observatory in Chile, and the extremely large telescope under construction in the same country, will add more. The Roman Space Telescope, planned for launch later this decade, will survey wide areas of the sky in detail that no instrument has ever achieved. For the moment, it is useful to sit with the uncertainty, to not rush to either of the two satisfying conclusions, the one that says everything is fine and the model is intact, or the one that says everything has changed and the textbooks need to be rewritten. The truth is almost certainly somewhere in between, and the slow process of discovering exactly where is itself part of what makes science worth doing. Consider, for a moment, where we are in this larger story. 100 years ago, the universe was thought to be static. Just under a century ago, we discovered it was expanding. 60 years ago, we found the leftover light of the Big Bang. 40 years ago, we confirmed the existence of dark matter through its gravitational effects. 25 years ago, we discovered dark energy. Each of these was a major revision to the picture of the universe held by the generation before. Each was, in its time, surprising. None of them came easily. All of them required careful, patient work over many years. In that context, the current tensions are not signs that physics is broken. They are signs that the next chapter is being written. The instruments are good enough now that we can measure things to a precision that was unimaginable a few decades ago. When measurements get more precise, small disagreements appear that used to be hidden inside the error bars. Sometimes those small disagreements turn out to be measurement errors. Sometimes they turn out to be the first hints of something genuinely new. The history of physics is full of moments where small disagreements grew into large insights. The slow drift of the perihelion of Mercury, a tiny shift in its orbit that did not quite match Newtonian predictions, was for decades an unsolved minor mystery. When Einstein's general relativity was developed, it explained the drift exactly, as a natural consequence of the curvature of space and time near the Sun. The tiny anomaly turned out to be the universe whispering that there was more to gravity than Newton had captured. Whether the current tensions will turn out to be like Mercury's perihelion, an early signal of a deeper theory, or like other historical anomalies that eventually dissolved into measurement adjustments, is not yet known. It will likely take years to be sure. The community of cosmologists is doing what the community of cosmologists is supposed to do, continuing to gather data, continuing to refine the models, continuing to argue with each other in published papers and at conferences. The argument is the process. The slow, patient argument is how the picture eventually clarifies. Webb's role in all of this is one that, in some ways, fits the spirit of the questions it is helping to ask. It is an instrument designed to be patient. It does not produce instant results. Most of its most important observations are integrations, where it stares at the same patch of sky for hours, gathering photons one at a time, building up a picture so slowly that you would never see anything if you only looked for a moment. The faint signals from the early universe accumulate gradually in the detectors. The data is read out, calibrated, processed, and only then turned into the images and spectra that scientists analyze. A galaxy at a redshift of 14 is detected as a small handful of photons, gathered patiently over hours of observation, processed carefully through pipelines of software, and finally identified as something that, before Webb, would have been invisible to us. Each of those photons is light that left its source when the universe was very young, traveled across 13 billion years of expanding space, and arrived, after that long passage, at a telescope that humans had only just managed to put in place to catch it. The patience required to detect such a thing is, in its own way, the patience required to understand it. It would be a kind of mistake, looking at all of this, to be afraid that the universe is doing something unexpected. The universe is doing what it has always done. It is being more interesting than we expected. It is offering us hints, small disagreements, places where the picture does not quite line up. And the people who have devoted their lives to understanding it are doing their slow, careful work, one observation at a time. When we look at one of Webb's deep field images, we see thousands of galaxies in a patch of sky, no bigger than a grain of sand held at arm's length. Each one of those galaxies contains tens or hundreds of billions of stars. Many of them are surrounded by planets, and on at least some of those planets, somewhere in the vast collection, there are surely conditions for chemistry and weather and atmospheres. Whether any of those planets hold something we would recognize as life, we do not know. But the room for it is enormous. The questions Webb has raised about the early universe are not, in any real sense, threats to that wider picture. The universe is still here. It is still expanding. The galaxies are still doing what galaxies do, glowing and turning and forming and dying across spans of time we will never directly experience. Whether or not the specific values of the Hubble constant or the specific masses of the earliest galaxies require us to revise our model is a question about our description of the universe, not about the universe itself. The universe does not care about lambda CDM. It is what it is, and it has been what it is for billions of years before we were here to write equations about it. What Webb is helping us with, more than anything, is the slow work of catching up to it. We are a young species on a small rocky world in the suburbs of a mid-sized galaxy. We have been using instruments to study the universe for only a few hundred years. We have understood, in even broad terms, what the universe is made of for only a few decades. The fact that our current best models do not perfectly fit the most recent and most precise data is not a sign that our science has failed. It is a sign that our science is working, that we are now precise enough to see places where our understanding can grow. Sometime in the next decade or two, the picture will sharpen further. Some current ideas will be confirmed. Others will be set aside. New ideas will be proposed that we have not yet imagined. The model of the universe in the textbooks of the future will be different from the one in the textbooks today, and that future model will be different from the one after it. There is no final version. There is only a long, patient process of looking and listening and refining. If you could step back from all of this and see it from a great distance, you might notice that this is, in some ways, what humans have always done. We have looked up for as long as there have been people. We have wondered. We have invented stories, then equations, then telescopes, each one a little better than the last at making sense of what we see. The story of Webb is just the latest chapter. Behind it is a long line of mirrors and lenses and patient observers, stretching back through the centuries to Galileo, who first looked through a telescope at the moons of Jupiter and saw small, bright points moving around the planet, and realized that not everything in the heavens went around the Earth. The chapter we are in now is one in which we have built an instrument that can see almost to the beginning. Almost. The first few 100 million years of the universe are now accessible to us in a way they have never been before. We are not finished. There are still galaxies, almost certainly, that Webb has not yet found, deeper and older and stranger. The Hubble tension may sharpen further. The early galaxies may turn out to be even more unusual than they currently appear. Or all of these tensions may dissolve into careful measurement and gentle correction. We do not know yet. What we do know is that the work goes on. The mirror is still gathering light. The data is still flowing back. The papers are still being written. The arguments still being had. The models still being refined. Somewhere in those calculations and conversations, the future picture of the universe is slowly taking shape. It will not be unveiled in a single moment. It will be assembled piece by piece over the years to come, and it will be more beautiful and more strange than the picture we have today. The universe Einstein gave us was a beginning. What Webb is showing us is that we have not yet reached the end. We may never reach it. The questions outlast us, generation after generation, each one passing a slightly better understanding to the next. There is, in that long passing of the light, a quiet kind of peace. The galaxies will keep turning. The light will keep coming. And somewhere in the cold darkness between worlds, a mirror of gold will keep gathering it, one photon at a time, for as long as it can. Rest well.